We have learned in the previous modules that this two level system that is so useful in developing the concept of stimulated emission and spontaneous emission is actually useless as far as making lasers in real life are concerned. So, what we will see in this module is what happens when we have more levels than 2. But before going there, let me ask a question about two level system. See, the way we introduced it was that when you perform the semi classical treatment using perturbation theory, time dependent perturbation theory, then you get an idea about absorption and stimulated emission. And then we said that it was the genius of Einstein that brought in the spontaneous emission term in the kinetic equations he wrote, because it is there, it is real. But I hope you have not forgotten that we also made a passing comment that even then the picture is not complete. Can you tell me why we made that statement? Why is the picture not complete for even a two state system, even if you consider absorption, stimulated emission and spontaneous emission? What have we missed out on? Yes, so we have missed out on something that is actually the focus of our research entirely. We have missed out on the non-radiative relaxation. Even in Einstein's treatment, non-radiative relaxation was not there. So, that comes in as yet another term in the kinetic equations, and when you bring it in, then you get all those relations we have written earlier, the rate constant of non-radiative processes, quantum yield and lifetime. They are related, right, 1 minus phi f divided by tau f. So, that is where that comes from, but in the discussion that we are doing so far, we are pretending as if there is no non-radiative relaxation, which of course is not correct and it does not give you a complete picture. But in the discussion that we are going to do now, we are going to invoke rather non-radiative processes to understand the situation, albeit qualitatively. I mean, one can go ahead and do a lot more kinetic equations and convince ourselves what the situation really is for a 3 level and 4 level system, but once you have done 2 level system, rest of it is just an extension, you can do it yourself. So, we will not try to do it in the course. I will draw the picture, perform a qualitative discussion and then move further ahead. Okay. So, 2 level system, as we said, is not good enough to give you net stimulated emission. Okay. What about a 3 level system? Suppose I have another energy level 3 and as said, we are going to perform a qualitative description here. And the situation is this, that you promote the molecule from energy level 1 to energy level 2, and let us say that there is some efficient non-radiative relaxation pathway that quickly brings the system down to level number 3. If you read textbooks on laser, in many cases they have not used the discussion of non-radiative pathway, they have stuck to discussion of radiative pathway, and it might as well be. There may be a radiative transition from 2 to 3, the only condition is that it has to be fast. Then what happens? And let us say, so an example that we will all understand is, let us say that state 1 is S0, ground singlet state, state 2 is S1, excited singlet state, state 3 is a triplet state. So, in that case this non-radiative process would be ISC, and as you know ISC can actually be promoted by using heavy atoms and all. Okay. There are mechanisms by which you can actually make ISC very efficient. Of course, purists would say that in that case the state number 3 is no longer a triplet, because when you invoke a heavy atom effect, then what you have is you have spin orbit coupling and it is no longer a pure triplet state. But that is fine, I mean we can still go ahead with the fact remains that it is not so easy for the system to come back from 3 to 1 anyway. So, as we know triplets have a long lifetime. So, it is sort of a quasi permanent state, right. Then what will happen? Let us say that this process takes place in a few femtoseconds or few picoseconds, let us say, and let us say that this state number 3 has a lifetime of let us say microsecond. Microsecond is enough. How many picoseconds are there in a microsecond? 2 picoseconds are there in 1 microsecond. Please come back to the linear world. Yeah, so can we try again? How many picoseconds are there in a microsecond? 10 to the power 6, right? 10 to the power 6. So, what I am trying to say is that before a molecule can come down from 3 to 1, if these are the lifetimes, a large population of 3 can actually be built up. If this process 2 to 3, radiative or non-radiative whatever, takes place in picosecond time scale, and if lifetime of this is microsecond also, then before a molecule that goes here can come down to the ground state, this 2 to 3 conversion will take place maybe 10 to the power 6 times, and 10 to the power 6 is a large number. So, what is happening? For a sufficiently long lifetime of this state number 3, its population will build up N3 and N1 will keep decreasing, okay? Is that right? So, what you are doing essentially is that you are pumping population from state 1 to state 3 through state 2, and if this 2 to 3 relaxation is fast enough, and if state 3 is sufficiently long lived, then you can achieve a situation, can reach a situation where N3 can become greater than N1, and then you can get spontaneous emission between 3 and 1. Is that right? Have you understood what is going on? So, for what we have discussed now, N2 is populated from N1, we can say instantaneously. Time for transition is attoseconds. From 2 to 3, that population takes place very efficiently, okay, femtosecond process, let us say. What we are saying is 3 is very, very long lived. If all the numbers work out nicely, and that is you can get an actual feel of the numbers if you work out the differential equations, then you can hope to achieve population inversion between 3 and 1, and once that is achieved, you can have lasing. Has everybody understood? And that brings us to something that is very, very relevant to our core discussion, that of a pulsed laser. So, you see, as long as, so initially think of time 0, population of state 3, level 3 is 0, population of level 1 is almost n total. Now, think of say 1 nanosecond after you have started, light is shining, right, the pumping light 1 to 2, that is shining. What N3 is building up, but still perhaps it has not reached population inversion. So, for the first 1 nanosecond there is no lasing, for 2 nanosecond also maybe there is no lasing, maybe after 500 nanosecond or 1 microsecond or 5 microsecond, provided lifetime of 3 is long enough, population inversion will be achieved. So, if you think of the output of the laser, there is no lasing for a long time, right, but when population inversion is achieved, this is the important part, then all the population will want to get depleted by stimulated emission at one go, right. So, the output you will get will be something like this. And then again, if this 1 to 2 radiation is on, population of N3 will keep building up and the laser will be silent. X axis is time, y axis we can say is intensity or something. Keep going, then after the required amount of time, once again there will be a burst of light and this will go on, provided you keep the pumping on. So, for a 3-level system like this, where 2 to 3 transition is ultra fast and 3 is ultra long lived, you are going to get a pulsed output. Case in point, ruby laser. So, this is one situation. Now, we will come back to level 3 also, level 3 once again, but let us talk about 4-level system first. Let us say I have a situation like this 1, 2, then let us say there is 3 and 4. And situation is like this, direct transition is possible between 1 and 2. From 2 to 3 you have an efficient non-radiative pathway. From 4 to 1 also you have an efficient non-radiative pathway. Can you actually have a system like this? Well, suppose you have intramolecular proton transfer, excited state intramolecular proton transfer, right? Then it is possible. Then if you look at the energy profile, then most likely it is going to be like this. Okay. So, I will draw a schematic molecule, some OH is there and a nitrogen atom is there. Okay. I am not even drawing the rest of the molecule here. So, what I am saying is this is the ground state corresponding to it. Then you excite, and in excited state proton gets transferred to nitrogen, excited state intramolecular proton transfer. So, if, okay, even before going there, if ground state this is the situation, what I am saying is that nitrogen being protonated, that is not an energetically favorable situation. So, that is when you have this asymmetric double well potential. Y axis is potential energy, right. What is x axis? You can say bond length for now or reaction coordinate. So, you have asymmetric double well potential. What happens when you excite? As we might have discussed in this course, acids are more acidic, bases are more basic in the excited state. OH is an acidic group, N is a basic group. In the excited state, due to change in acidity and basicity, proton gets transferred. So, now this locally excited state for this one is no longer energetically stable. So, when you excite, then you are going to reach a state that is actually energetically less stable. So, excited state potential energy surface you can expect is something like this. This state is OH double bonded to N. This excited state is also OH not double bonded, hydrogen bonded to N. Then proton transfer has taken place. This is hydrogen is covalently bonded to N, hydrogen bonded to oxygen. This is the corresponding ground state. Okay. So, if proton transfer is sufficiently facile, what will happen? You excite, immediately proton transfer will take place, and then whatever emission takes place will be from here to here. But then since this is energetically not favorable, the moment it has any population, it will come back to this 4-level system. So, that is why ESIPT molecules have been touted for a long time as good candidates for making lasers, because they are actually 4-level system. But now see what kind of output we will get. Let us write. When you start, population of N1 of 1 is N1. What is population of 2? 0. This is 0, this is 0. A little while later, so N1 equal to N total, you start from that. A little while later, what happens? This decreases a little bit. Population of N2 is still 0, because there is an efficient non-radiative pathway to level number 3. All right. Level number 3, let us say, has some lifetime, whatever. So, N3 population is there. What about N4? What we are saying is, if you look at this diagram, The moment level 4 is populated, it goes back to 1. So, N4 population is maintained to close to 0 at all times. This is important to understand. Here, if the rate constants are such that N4 concentration is held to be near 0 at all times, then what will happen? Population inversion is already achieved between third level and fourth level, because even if there is like 2 molecules in N3, population of fourth level is 0, right. So, in this case, what kind of an output you get? There might be an initial induction time, but if you neglect that, you get a continuous output. So, this is an example of the first one, third level, 3 level system is an example of an intrinsically pulsed laser. This is an example of an intrinsically continuous wave laser. So, I told you an example of a 3 level system that is actually something like this. Does anybody know an example of a 4 level system? Something is very common and not necessarily in ultrafast, which I do not exactly know, it must be a diode laser. So, yes, most likely yes, Nd:YAG laser is what I had in my mind. Nd:YAG laser is perhaps the most celebrated example of a 4 level laser. So, it is supposed to be continuous, right. So, you see that Nd:YAG lasers are there that have continuous wave output, and then you see Nd:YAG lasers that are pulsed. So, what I am trying to say is Nd:YAG lasers are actually intrinsically not pulsed, intrinsically they are CW lasers. If you want to make them pulsed, if you want to get pulses out of them, then you have to do something yourself, and that doing something yourself is either Q switching or mode locking. So, that is what we are going to learn in the subsequent modules. Maybe not very sure whether it will be exactly in the next module. I have not made up my mind yet how much I want to talk about gain and loss and Q factor. Perhaps we should do a little bit, but eventually we are going to talk about mode locking. Okay? So, remember, something that is intrinsically CW can perforce be made to give you a pulsed output. Okay? And it is not very difficult to understand as well. The light coming from that lamp is CW, right, and the detector I have is my eye. So, I keep it shut, I do not see it, then I open it for a small time and close it again. So, that way the detector that I have actually gets pulse light out of a CW source, right. Or I could use a shutter, well my eyelid is a shutter, okay. But here I cheated a little bit because I talked about shuttering the detector rather than the laser itself. What I can do is, maybe I can keep it off for some time, turn on the switch only for a short time periodically. That may not be a very good thing to do because it might spoil it, but there are other ways. We can use different kinds of shutters by which a CW light can be made pulsed, and that is what we will learn in detail, because that is really something that is very important to our course of study. But before we leave this discussion, let me talk about another kind of 3 level system. When I say another kind, 3 level system has to have 3 levels, cannot really help there. What I cannot really do much about 2 to 3 also. But suppose now I have something in which this 2 to 3 conversion is radiative and 2 has a long lifetime. Three to 1 is non-radiative and fast. Of course, there is a catch here. The catch is, what about 2 to 1 emission? We will come to that. But for the moment, you tell me, if this is the situation, then what will happen? What kind of laser do I get? First of all, this is where the lasing will take place, right, between 2 and 3. Will it be CW? Will it be pulsed? It will be CW. So, you can have 3 level systems in which the output is continuous wave. It is not necessary that whenever you have a 3 level system, the output is going to be pulsed. It all depends on the relative rate constants. Okay? But now, who will take care of the 2 to 1? 1 to 2 absorption is taking place. So, 2 to 1 can also take place, and I am trying to have induced emission. So, do I have some way in which I can force the system to give me lasing in 2 to 3 and not 2 to 1? Yes. So, energy density matters, right? Do not forget, energy density is another factor here. So, if energy density of nu 2 1 is very low and energy density of 2 to 3 is high, maybe you introduce some photons from somewhere of that energy, then you can make a laser emitting in that particular frequency. And this is actually discussed in Macquarie and Simon's book. In my edition, the page number is 603. Here they have talked about a 3 level system, and you see they have considered all kinds of, if you look carefully, there is no non-radiative transition here. It is radiative all the way, but they have set the conditions in such a way that you have a 3 level system where the lasing is between 3 and 2 and the output is continuous wave. Okay. So, I would advise you to try and work out these problems. You see, finally, you get an expression of N3 by N2 and so on and so forth. So, do it yourself and satisfy yourselves that this is actually the case. Okay. We will move on a little bit and give you a quick glimpse of what is to come. Okay. And let me show you, since I have the book open, instead of drawing, let me just show you the diagram. This is what you have inside a laser. I think this is something that all of us know. How do you make a laser? How do you get amplification? What you do is, first of all, you need some pump source. You have to create that appropriate excited state. Pumping can be done either optically or electrically. You can have some light source. So, if you see older Nd:YAG lasers, they use flash lamp to excite. So, in the laser that I used as a PhD student, had this Nd:YAG rod about this big, and on 2 sides there were 2 flash lamps. So, the arrangement was like this, parallel. You can think that the blue pen, you better look at the projection, then you will see. Blue pen is the YAG rod, and let us say the black pen is a flash lamp, and you have another flash lamp on the other side, and we had this parabolic mirror. So, light from here would be focused onto the YAG rod. Of course, 25-30 years ago, things were much more primitive than what they are today, and there was always this problem of heating. You have this flash lamp on all the time and it is pumping, so things would get heated. How do you dissipate the heat? There was this actually very nice, if a little cumbersome design, where this whole thing was immersed in a tub of water. A tub is about this big. The whole thing was in water. So, of course, that water had to be distilled water, and then constant temperature had to be maintained. So, there was secondary cooling and all. But you know, if you use a bulb, sometime or the other it goes bad, and if you are unlucky, these flash lamps, instead of just dying on you, would burst. And then whether they burst or not, to change the flash lamp, we had to take out like 12-13 screws, drain the water completely, then salvage broken pieces or the unbroken flash lamp from there and change it. So, those were more interesting days. So, that is one way of pumping. What we do now in diode pumped solid state lasers is that you have a diode bank which gives you light, which is directed by photodiode onto the YAG laser. And whoever has used that laser would know that there is a chiller that provides cooling, but things are not as messy as they used to be earlier. Now, it is not necessary that you always do optical pumping, you can do electrical pumping as well, but let me decide whether we want to talk more about that later. And then you have this, I do not know if you can read the projection, here then you have this gain medium. Gain medium or active medium, that is the molecule or material or ion which actually gives the emission. So, if you are talking about ruby laser, your gain medium contains ruby. What is ruby? We will come to that a little later, I will show you if you can read. And then what you do is, all right, emission takes place, and that emission photon that are there, you have two mirrors on two sides. So, for photons that go to this mirror, and typically you have curved mirror, because you want to focus here, so that you have higher density of photons. So, let us think of one photon which has gone here, hit this mirror, come back, and when this photon passes through the gain medium, it is going to experience other ions or other molecules or other material that is excited already by the pump source. You get my point? First, think of it like this: pump source, let us think of it as excitation light, 1 to 2 excitation. Okay? I have done that, and some emission has taken place. Let us say it is stimulated, it is spontaneous emission, does not matter. It can take place in all directions, but we are talking about this mirror. So, a photon that goes and hits this mirror, comes back, retraces its path. Now, when the photon comes back to the gain medium, it is going to find other molecules or other ions, whatever the gain medium is, in excited state. Who has taken them to excited state? The pump source. Is that right? It is a pump source that is exciting the components of the gain medium. The job of the photon that is initially emitted and has come back is to cause either promotion of unexcited molecules or de-excitation of already excited molecules. This finds both. Okay? And that is where this discussion of gain and loss and all that comes in. Maybe we will do it later. So, think of this: photon comes, depopulates one ion or one atom or one molecule in the excited state through stimulated emission. The important thing to understand is what we had drawn at the beginning of the 16th, whatever it is called, 16th module or 16th lecture. Remember, the photon that comes in is not absorbed, it goes out itself, but it de-excites a molecule and causes the emission of a second photon. So, now you can think like this: a photon goes out by whatever mechanism of emission, comes back, causes stimulated emission. Now, two photons come here, hit this mirror, come back, and they cause two more photons to come out. So, in every round trip, the number sort of doubles in the best case scenario. It does not always double, it will always be less than 2 actually the factor, but it increases. Okay. So, in a very short time, okay, how much time does a round trip take? Let us say, let us do a simple calculation. Let us say this length is 1 meter. So, round trip would take how much? Start from here, okay, go here and come back, let us say, complete round trip. It is travelling 2 meter in that case. Okay, let us say 3 meter. Let us say 1.5 is the cavity length, then it is easier. Then round trip distance is 3 meter. What is the speed of light? 3 into 10 to the power 8 meters per second. This time we have not made a mistake. So, you can calculate how much time it takes, very small, right. So, if you are talking about some seconds, in a few seconds there is a huge amount, huge number of photons that is produced, okay? And that is called gain, increase in number of photons. But now, what is the point? I mean, see, if you are a miser, you work very hard, earn a lot of money, keep everything in an iron box, and then when your time in the earth is over, of what use is that money to you, right? So, you have to spend it also. So, if you are going to make a laser, it is not enough to just have a lot of gain, you have also need to have a little bit of loss. I mean, light should come out. And the easiest way in which it is done is that on one side you have a high reflective mirror, reflectance 100%. On the other side you have a partially reflecting mirror, so 95, 99% reflecting mirror, 1% will come out. Okay. This is called the output coupler. We will discuss these terms again in more detail. Okay. Then what will happen? So, initially when number of photons is small, you hardly see any output, because say 1% of light is coming out, let us say, I am being a little stringent here. But when there is a lot of gain, there is a build up, then 1% of that amount is also good enough. Then you get laser light coming out from this side. Okay. This is the simplest way in which you can depict a laser. Now, we will get into more complication. What happens? What should a cavity length be? I arbitrarily said 1 and then I said 1.5. Is it arbitrary? Can I have any laser light even for CW? And if I want pulsed light, what is the more stringent condition that comes? These are things that we will slowly get into, but let me complete this discussion by showing you another page of Macquarie. If you cannot read here, please go back and read in your home. This table 15.2 in Macquarie and Simon provides you a compendium of some solid state lasers, and what you see is chromium. So, it is important to understand what this is. We always say ND YAG laser and forget about it. It is important to remember what is the role of ND is and what the role of YAG is. What is YAG? Yttrium, aluminum, garnet. And what is that? It is actually Al5O15, okay? Y3 Al5O5. Have you heard the word garnet in any other context? It is a precious stone, jewelry, yes. Have you heard of ruby in some other context? Of course you have. Okay? So, all these precious stones are precious to us, not because we want to wear earrings, I mean not all of us, but because they actually make good gain media. But it is important to understand that it is the dopant, the iron, that is actually the emissive species. The role of YAG or YEL for glass, all that is to provide a support. In fact, when you talk about ruby laser, natural ruby does not give you good laser. Ruby laser invariably has synthetic ruby, which is grown so that the crystal structure is good and all. Natural ruby is not very easy to make use of as a laser material. So, here the last example that is discussed is our good old titanium sapphire laser. Here this Ti3 plus ion, that is what gives you the emission, okay? And sapphire, again another precious stone, is Al2O3, that is the matrix. Both are important. I mean, titanium in some other matrix may not be as stable as titanium sapphire. So, good thing about why are precious stones precious? I mean, let us say I make stone of sodium chloride, crystal of sodium chloride, I can call it a stone, right? It is not going to be very precious, or calcium carbonate, that is actually a valid stone. Why is it that calcium carbonate is not so precious as ruby? Because the answer is same as if I ask you why is gold precious, because gold does not react. You make very nice jewelry out of iron, then eventually they rust and it is not there anymore. Even silver gets black, but not as bad as iron. Gold does not react, that is why gold is so precious. Platinum is precious. So, here also these precious stones are precious because they are so stable. They do not react to the slightest moisture or some other gas that might be present. So, that is why you want to make these as support material. This is what your titanium sapphire laser actually is. And you can also have gases as gain media. You can Heaney laser is something that you might have heard. Before the advent of diode lasers, Heaney lasers were ubiquitous especially where alignment was involved. Now, in many cases they have been replaced by diode lasers, because now you have good quality diode lasers which give you nice transverse mode and all. Okay. But that will be discussed sometime later. The point I am trying to make here is that your gain medium can be many different things, can be solid, can be liquid, can be gas, but it has to satisfy certain properties, 3 level or 4 level at least, and stability is an issue. Do you know of any laser where the gain medium is liquid? Well, when I say liquid, I mean a solution. So, go to the next lab, you will see dye laser. So, what they do is they dissolve something like rhodamine 6G in methanol and keep it in cuvettes, excite using a green laser and make a laser out of it. Again, as PhD student, I used what is called a synchronously pumped dye laser. We will discuss what synchronous pumping is. There we used to flow the dye. We wanted picosecond resolution, you cannot use a cuvette. So, you actually flow the dye and you have a jet of dye coming out, and it is caught by a what is called a catcher tube, and that takes it back to the reservoir, and the green laser was focused onto that jet of the dye, like no medium, so that it does not become broad. That was also rhodamine 6G, but not dissolved in methanol, it dissolved in some viscous solvent, so that the jet is good. Okay. So, we will come to those one by one. I wanted to do a calculation today, but maybe we will leave it for a little later when we actually discuss dye sapphire laser, right. So, next day onwards we talk a little more about lasers, and finally, we are going to arrive at pulse lasers.